Bear with me here, it's going to sound like you're in the wrong class for a moment. Do you remember contour lines, contour maps, the maps of elevation where you have all these different lines that show lines of equal elevation? They look like this. So these are contour lines, and this shows a hill with a flat top. And you can see that basically just by looking, right? So some things about these lines, they're lines of equal elevation, right? They form closed loops, they never cross, and where they're bunched up super close together, that's where you know the hill is steepest, right? Well, Michael Faraday saw a parallel between the behavior of, say, water flowing with gravity and with electricity, and that parallel carried through to some really important connections. Faraday determined that there was something analogous to height, only with electricity instead of gravity, and he gave it a name that we really don't use anymore. He called it the electromotive force. And the electromotive force later got renamed to electric potential difference because it's not really a force. And it is very much like height for charge. If you have high height here and low height here, water will naturally flow down there, right? If you have high voltage here and low voltage here, then positive charge will naturally flow this way. Now, you don't have negative water that can flow uphill, but we do have negative electricity that can flow the other way. So this idea of electric potential difference is a really important one. And so you can think of height as like the energy per weight of an object. And you can think of electric potential difference as the energy per charge. Now, electric potential difference is the correct name, but people get lazy. They call it potential difference, they call it electric potential. And because we measure it in volts, after Alessandro Giuseppe Antonio Anastasio Volta, because we call them volts, it's very commonly referred to as voltage. The old name electromotive force comes up now and then, but because it's not really a force, people don't really use that anymore, but they will use the abbreviation EMF. All of these things are voltage. All of them are electric potential difference. So check this out. We've got a couple of charges here, and I want to point out these lines here of equal voltage. They're called equipotential lines. Each one is at the same voltage. Where they're bunched together super tight, they show you where the flow is going to be extra strong. They're all perpendicular to the flow of the electricity. They form closed loops. They never cross. They're extremely similar to equal elevation lines on a contour map. So a volt being the energy per charge. Here's what the equations look like on both the Regents and AP reference tables. Okay, they do look a little different, but they are the same thing. This idea of voltage allows us to use a simple idea of how many volts difference between two spots and apply that using the work energy theorem in order to solve problems. So here's an example of that. So suppose you wanted to build an old school tube TV, which is a particle accelerator for electrons. It speeds the electrons up and then slams them into a screen with little phosphorescent things that glow when they get slammed into by electrons with enough energy. So suppose you wanted an electron to go 5 times 10 to the 7 meters per second, which is pretty darn fast. Supposing you wanted that, how much voltage would that take? It's actually quite easy to figure that out using conservation of energy or the work energy theorem. So if we come up here and we say that the initial energy plus or minus work equals the final energy, right? We can say, well, the electron's just hanging out doing its thing on the surface of a metal, so it doesn't have any initial energy. And then work is QV. What kind of energy does it have at the end? It has kinetic energy. And so that's pretty much it. Just divide this over and substitute in. You get your voltage that you need is 1/2 mv squared divided by the charge of the electron, which is E, right? So 1/2 mv squared divided by E. Just plug in your numbers and you're done. And by the way, there was another way to think about this problem too. If you started with initial energy plus or minus work equals final energy, you could say, well, I set up the voltage already, which gave this thing some potential energy, and then there's no work from outside the system.
The potential energy is QV. Those of you taking AP Physics 2, your equation is potential energy equals QV rather than voltage equals work over charge. They're literally the same equation, but they look rather different, don't they? So QV equals 1/2 mv squared, and you go from there. It's the same thing.
This parallel between voltage and gravity goes even further. AP2 students, you saw the electric field equation with Gauss's law in the previous video. The rest of you don't worry about that. But so you have electric force and you have gravitational force, right? Gm1 m2 over r squared versus kq1 q2 over r squared. They're very similar, yes? Well, the potential energy due to gravity is, well, potential energy, work is force times distance. Get rid of one of the distances, you get Gmm over r. Well, potential energy for electricity, kqq over r. That's the potential energy from two charges that are a certain distance apart from each other. The electric field is like the gravitational field strength, which we would just call G, right? The electric field is kq over r squared. For gravity, it's Gm over r squared. So you have all these parallels. This last one, voltage, for a point charge, if you have a point charge, that's sort of the peak of a mountain, or a negative point charge would be the bottom of a pit in an elevation map. And so that electric potential from a point charge is kq over r. That is directly analogous to height. It is important to point out that just like height is scalar, so is voltage. If you envision a big sheet and you grab it and you pull up a certain amount, that would make some sort of voltage, and you get this kind of swooping mountain because you pulled it up. If I grab here and I pull up, I get a swooping mountain again, right? And the spot in between is going to be even higher. How much higher is it going to be? It's going to be the voltage from this one, well, the height from this one, plus the height from this one. They add up as scalars. So we'll do a quick example of that just to show you how easy that is.
Suppose I have a charge here of 1 nanocoulomb, and I have another charge over here of 1 nanocoulomb, and I have a charge down here of 2 nanocoulombs. And I want to know, what is this voltage in this spot right in the middle, which is 1 meter away from each of them. Now, when you see this, your first thought might be, oh no, all these angles and things, I'm going to have to do some sines and cosines and split things into vector components, and you don't. Voltage is scalar. This equation is V equals kq over r. And because there are 3 of them here, you just have to do that for each one. We get 9 times 4 is 36 volts. Done. That is as easy as this is. If the 2 nanocoulomb were negative, then this would become negative right here, and this whole thing would become 0, and the answer at this spot here would be 0 volts. It's that simple. They're just scalars. You calculate them and add them up.
So there you have it. There's the relationship between electricity and electric potential difference and energy. Remember, electric potential difference is not electrical potential energy. It's related, not the same thing. So if you prefer electricity, voltage, and energy, there you go. In our final video on electrostatics, it's really just intended for the AP2 class, but we're going to talk about how to store electrical energy in something other than a battery. You can actually store the electrical energy directly in a capacitor, and you can check that out in the next video.